Yes, we are now introducing ourselves to errors, which will take us to what we call error propagation. So the bit of the errors that we studied before, it was a bit that we can use to deal with the trapezium rule. Now, if we are dealing with the error propagation, then this is very important. The error propagation always covers the errors to do with the errors that are found in different expressions and also estimated values. Yeah, so an error, we are saying and we are not changing that it is the degree of inexactness, or it is the difference between the exact value and an approximate value. So error is equal to exact value minus the approximate value. So because we are saying that we want to see how to generate errors in expressions, so if capital X is an exact value and small x is an approximate value, then the errors that we are going to study in this topic, the errors are found in approximate values. So if capital X is the exact, then you cannot have an error in an exact value, but the error will instead be found in an approximate value, small x. So that is why we are saying that error in small x is denoted by all these ones. I used to denote the errors in an approximate value or in approximate values. So we are saying small x because we have noted that small x is an approximate value and our error must be in the approximate value and not in the exact value. So our error in small x can be denoted by rho x, small ex, delta x, capital Ex, or E1, as the case may require. So for us, we are choosing to use delta x, but you can use any of these ones to denote the error in an approximate value. Or the question will dictate the symbol to use. Sometimes they may even use h. But if they do not, then you are free to let and use that letter or that denotation that you will have supposed. So our error in small x is exact minus the approximation. Because we do not have errors in exact, we want to see how we can make the exact the subject. So if we denote our error in x with delta x, so delta x will be the exact, which exact is capital X, minus the approximation, which approximate value is small x. So if we make capital X the subject, we are going to have x plus delta x. We begin with the approximate plus followed by the error in it. So this is an expression of the exact value in terms of the approximate and the error, as we shall see when we reach the in-depth of the error propagation. So some of the sources of errors are experiments. There are some physics experiments which we carry out and we fail to get the correct final answers, but instead we get approximate values which are very close to the exact because of some factors. Also in chemistry, there are some experiments which prohibit us from getting the exact values. So all those sources of errors, one of the sources of errors is the experiments which we carry out in different subjects. Then we also have using a few steps of an approximate formula. If you do not use all the steps in the formula, then you're also bound to get the the approximate value, but not the exact value of the the expression. For example, in the trapezium rule that we used, we found out that if you choose not to use very many sub-intervals and instead you terminate and use a few sub-intervals, then the error in your final answer becomes very big. And if you reduce to reduce the error, you instead create very many sub-intervals. So if you use a few, you get an error in the final answer. If you use very many, then you are bound to getting the the exact value, or a value which has a very small error in it. So using a few steps of an approximate formula also causes an error. Then there is also what we call rounding off, which we studied in senior 4, and also the truncation, which we are going to see how it is supposed to be done. So we are beginning with rounding off and the truncation because we saw this in the trapezium rule. The class also looked at experiments in the different subjects. So rounding off refers to writing or expressing a number correct to a given number of decimal places or significant figures. Decimal places, these are number of positions that appear after the decimal point. For example, all the values which appear on the right hand side after the decimal point, they give what we call the decimal places. If you have a number 50.32, our decimal point is here. So immediately after the decimal point, that is where we stand and count the decimal places. It is 1, 2. So this expression has 2 decimal places. Now when you go to the second expression, which is a 90, we do not have any decimal point there, and because it is 90 without the decimal point, then this one has 0 decimal places because it is a whole number without any decimal point. You will think about 568.3042 and you write the number of decimal places which are there. You also think about 111,360.0 and you write the number of decimal places which we shall find there. Now away from that, we can now go to what we call the significant figures. Significant figures are the non-zero numbers. However, there are also some zeros which are regarded to be significant. So all the zeros that appear before rounding off are significant. That is in the first note. All the zeros that appear before rounding off are significant. Then 2, all the zeros that lie between two non-zero numbers are also significant. All the zeros which will appear between the non-zero numbers are significant. Then all the zeros that are going to appear not only between the two, but between the non-zero numbers, we can remove this and say all the zeros that appear between the non-zero numbers are significant. Then all the zeros that come after a non-zero number before rounding off are said to be significant. You underline the word before rounding off, and then appearing after. They are appearing after a non-zero number. If the zeros are appearing after a non-zero number before rounding off, they are said to be significant. If zeros are lying between non-zero numbers, then they are also regarded to be significant. In this trial example activity, they want us to state the number of significant figures in each of the following. We count the significant figures from the left going to the right. In this we are beginning from the left. This is non-zero, it is a 5, so it is significant. There are 1, 2, 3, 4 significant figures. This is 10,000. Because these zeros are appearing after the non-zero number, which is a 1, then it means all these zeros are also significant. So we are going to count them from the left. We have 1, 2, 3, 4, 5 significant figures. This 0 is lying between non-zero numbers, so it is also significant. We count from the left. There are 1, 2, 3 significant figures. So in this, we are going to have 1, 2, 3, 4, 5, 6, 7, 8 significant figures. All these zeros are significant. This is significant because it is coming after non-zero numbers. Then these zeros are also significant because they are lying between non-zero numbers. Now in this one, we have 0.0034. These zeros that appear before the non-zero numbers are all not significant. So we are going to count them from the left. So we shall have 1, 2, because all these ones are not significant. So this has two significant figures. You will think about this and that, and you write the number of significant figures which are there. Now in the example, they want us to round off the following correct to the required number of decimal places or significant figures. So in part A, you have 6.34 and they want it to one decimal place. We said you go to this immediately after the decimal point, you count the number of decimal places. So it is 1, 2, but they want it correct to one decimal place. So this is the one decimal place they want. After the decimal point, count only one decimal place. You look at the value after the one decimal place. If it is from 0 to 4, you add a 0 to this one. If it is from 5 to 9, then you add 1. And because this is a 4, we shall add a 0 to make it a 6.3. We are writing this same expression to one significant figure. So it is a 6.34. We count significant figures from the left. This is 1. So this is the one significant figure. We examine the value before. If it is from 0 to 4, we add a 0. And if it is from 5 to 9, we add a 1. And because this is a 3, we shall add a 0 to make it a 6. In brackets, you put one significant figure. In part B, we have 634.6845. They want it to 3 decimal places. After the decimal point, you count the number of decimal places. We have 1, 2, 3. So these are the decimal places which they want us to reduce the expression to, or the value to. You examine this value. If it is from 0 to 4, you add a 0. If it is from 5 to 9, you add a 1. So the final answer becomes 634.685 in brackets 3 decimal places. But if they want it to 3 significant figures, then you count the number of significant figures from the left. We have 1, 2, 3 significant figures. You examine the value before. If it is from 5 to 9, you add a 1. If it is from 0 to 4, you add a 0. And because this is a 6, we shall add a 1 to make it 6, 3, and a 5. So it is 635. We go to part C. We have this. It is 0.003480 to 2 decimal places. So we said we count the number of decimal places immediately after the decimal point. They are 1, 2. So we want this to 1, 2 decimal places. We examine the value immediately after the 2 decimal places. It is a 3, and because it is a 3, we add a 0 on this to make it a 0.00, and this is our final answer. If they want it to 2 significant figures, we say all the zeros that appear before the non-zero numbers are non-significant. So all this and that, they are non-significant. But then we have this other 0. For it is significant because it is appearing after a non-zero number. But we count significant figures from the left. So non-significant, non-significant, non-significant. They are 1, 2. So these are the 2 significant figures. Now we examine the value after. If it is from 5 to 9, we add a 1. And because it is 8, we shall add a 1. And this will become 0.0035 to significant figures. We now have part D, which is 1608 to 2 decimal places. This is a whole number. So if we are to write it to 2 decimal places, then we create 2 zeros immediately after the decimal point to have it correct to 2 decimal places. So it is 1608.00 to 2 decimal places. If they want the same value to 2 significant figures, this is an answer. If they want the same value to 2 significant figures, we count them from the left. It is 1, 2. We examine the value after it is a 0, so we add a 0 here. Now, because this value does not contain a decimal point, then we maintain all these other values after writing it to the 2 significant figures. We maintain these other values with the zeros. So we shall have 1600. 1600 is going to be our answer, not 16. If you write 16, it is going to be wrong because it is very far from this. So we write 1600. When somebody gets to this, because we said all the zeros that appear after rounding off are non-significant, this is not significant, this is not significant, but it has only 1, 2 significant figures. So you must take note of this. There are some values which they give us and they want us to write them to some significant figures, but when they are bigger values, so we maintain the other values with the zeros. Then in part E, we have 1000 to 2 decimal places. It will be that, and 1000 to significant figures. It is going to be definitely this. So there are 1, 2. This has 1, 2, 3, 4 significant figures. But if you want it to 2 significant figures, it will be 1, 2. Because this is a 0, then we shall add a 0 on this to make it 1, 0. Then we maintain the others with only zeros. So it will remain as 1000 to 2 significant figures. You will try out this and this as an exercise. Now there is also what we call truncation. Truncation means to terminate an expression to a finite number of steps. Terminating of a value to a finite stated number of decimal places or significant figures is what we call truncating. You do not examine the impact of the value that comes after. For example, if they tell us to truncate the following to the given number of decimal places or significant figures, we have 6.34. They want it to 1 decimal place. You just count 1 decimal place. It is a 3. You don't look at this. Just write 6.3, then 1 dp. If they want it to 1 significant figure, you just count the 1 significant figure. It is 1. You don't look at the other. You write 6, then 1 significant figure. Part B, it is 634.6845 to 3 decimal places. You count the number of decimal places. There are 1, 2, 3. You don't look at this one because we are cutting off. So it will be 634.684 in brackets 3 decimal places. The same applies to this part. After counting the significant figures, you do not examine the impact of the value that comes after. You just terminate at that point. If it is this, you will follow the same logic. If it is 1000, we follow the same logic. So you will try out to this and also this, and then you share on my email or WhatsApp. Thank you for listening. The email is asmanmutiaba4@gmail.com and the WhatsApp is 0701 600 343. Do not forget to subscribe to this channel for more series. Thank you for listening.